Okay. Let's talk a little bit more about diagnostics. Now, we've shown you all of these wonderful plots like this that I before, and of course the question is, how on earth do I generate this from the data that the model outputs? So as I said, all of these diagnostics we're plotting here are generated from AIJ files. So as you write your monthly output from your model, January, February, March for year 1, January, February, March, blah, 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 the year 5000 or orbit 5000, whatever it is, you're going to generate a directory full of ACC files. And so what some of us have done is we've written our own kind of custom scripts that first of all generate AIJ files from all of the ACC files in our directory tree, in that directory tree that we're interested in. And then we run some other scripts that extract this data that we're interested in. And that data is basically extracted using NCDump, which is one of the tools that you should have installed or compiled for the tutorial. So I'll just show you what the command is, and then I'll show you one of my scripts that I myself use to generate this kind of data. So the basic of the command is for the net rate of balance, for example, is net_rad planet underscore hemis. So V tells the netcdf file, give me this variable from the netcdf file. I have to give it the netcdf file name, and I didn't do that. I have to generate the AIJ file. This is just the first time step file, just to show you how it works. So let me do it again. NCDump.
I just want to mention that NCDump is a standard feature which comes with netcdf.
Yeah. So when you installed NCO tools, it should have come.
No, it's not library.
NCDF.
NetCDF library. It's not NCO.
Oh, it's an NCF.
Yeah.
Okay, which you should have installed.
So you always just have it. I mean, otherwise you will not be able to compile the.
Yes.
Yeah.
So here's what the end of this file looks like, and of course, how about that? Because I haven't loaded my modules. Here we go. Supercomputer. So as I mentioned before, the first variable is the southern hemisphere, northern hemisphere, and the global mean. So I have a script that basically pulls out that third number from every single AIJ monthly file I've generated from my data using this netcdf or this NCDump command. Now this is what one of those scripts look like. I have a lot of these scripts for different purposes, but this is basically just a really simple Unix bash script that I use. You can use any language you want. I don't care. If you want to use Python, if you want to use Julia, if you want to use MATLAB, you can use whatever suits your needs, whatever you're most comfortable with, whatever you're most comfortable with. I'm an old dude, and I love writing bash scripts because they're simple and they run on every single Unix platform that has ever existed for the last 40 years, because I've run on every platform for the last 40 years. So I can say that with some confidence. Well, almost 40 years. I was maybe 30 exact. Anyway, so here's an example of what my script in particular looks like. I should make maybe my font a little smaller so I can put this all on the screen here so everybody online can also see it. So there are other ways to do this. My way may not be the best way, but it works. But basically what it's doing in this case is I tell it, I write a little for loop here, and I tell it to look at, first of all, I have to generate my AIC files. So I tell it to list all of my ACC files ranked by time, because I need to do it in a sequential order in time. Because if I just type LS and I pipe it through there, it's going to do it alphabetically. And that's not very useful. I don't want to do it alphabetically. I want to do it by the timestamp. So that's what this ls-tr, it says list every ACC file by the timestamp. And then I tell it to run the scale ACC command. You can see that I'm not running what you know as the scale ACC command. This is a custom built scale ACC, which I will not go into, but it doesn't matter. The point is it's still the scale ACC command. The $I in this case takes the ACC file from the LS output, tells it to generate an AIJ file, and then tell me that it's run the command. So the first line in the script just generates all your AIJ files in a sequential time order. Okay. Then all of the rest of the lines here are using the dump command to pull out the Hemis variables that I'm interested in. So the first one is the one I just showed you in the other window, where for every AIJ file, I tell it to dump out the plan, or well, the first one I have here, planetary albedo, for example. That's one of the diagnostics I'm interested in. And I tell it to grab that planetary albedo and dump it into a text file. So it dumps those 3 hemispheric variables, southern, or was it northern, southern, and global, into a text file. And I do that for all of the variables, Hemis variables of interest to me. You might have others that you're interested in, but these are just the ones that I use. I'll gladly share one of these scripts with you if you want it. Just write me. It's no problem. It's just a bash script. You can copy it, modify it, destroy it, make your own Python version, whatever you want. But if it doesn't work, don't complain to me. Figure it out. We're all adults. So you can see all kinds of stuff here. For example, this one down here, MWL Hemis, that's the mass of the water in lakes. That's very useful to understand if your lakes have stopped growing or shrinking in time, whether the mass of the water in the lakes is changing. Here's that net red planet Hemis I just showed you. Ocean ice fraction, that's another one I use. Sometimes I'm interested in precipitation. Q100, that's the humidity in the top layer of the model. People are interested in that for various reasons, which I won't go into, etc. So it generates all of these text files. And then I use another old school Unix tool called awk to just pull out the global value.
Oh, really?
Awk is
oh my God.
Awk is God.
Yes.
Yeah. If God lived, he would be awk. Yeah, sorry, old timers, you can't get away from it. Anyway, it doesn't matter. The point is, you can just use what I've output here in this very simple text file, and you can use whatever plotting tool you want to plot this up, as I have done. Again, I used to work 20 years ago with a lot of machine learning and statistics people, and they used to just love MATLAB, and I have been wedded to MATLAB ever since then. So I use MATLAB to read my scripts. But you know, the big thing 10 years ago was Python, and now it's Julia. You can use whatever you want to plot this stuff up, whatever suits your fancy, whatever diagnostic variable you want.
Or if you're old school, you could just use GNU plot, and then you don't even need to use awk. You can plot.
You don't need awk. Awk is another post-processing from these files. You can use whatever you want.
Plot this files just
right. It's just that MATLAB's a little bit fussy about the numbers. That's why I use awk. Anyway, you can use whatever you want to plot this data up, but you're going to have to do it. So get comfortable with it. Now, there is some I/O overhead with this stuff. So if you're on a big supercomputing place and you're on a big file system, you're going to be doing a lot of I/O here, and it'll take a while. So if you have, say, 10,000 orbits and you have 12 months in each orbit, it might take a few hours for the first line of this command to run to generate all your AIJ files. The AIJ files are smaller than the ACC files, but they also take up disk space. So be careful, just as a heads up, about what you're doing. You don't want to overload everybody else's file system or go over your quota or whatever it is.
I'm sorry, could you remind me, at what frequency are those .nc files generated?
Every month.
Once a month.
So every orbit, you get 12, January through December.
So that script is extracting one line from each one of the NC files.
Yes.
For every month, putting it all into those text files.
Yep.
Could you do a quick one of those?
Yes, I can. Well, no, I can't because I don't have them here, but I'll find one. Let me think where I have some located. Let's see here. Where do I have one of these? Sorry, you're going to have to hear my machine going. No, it's okay. Let's see. Maybe it's hiding in here. I have like one file thing.
Do you want some years of
No, I just have to find. Oh, wait, here's one. Maybe this works.
Mine are in Python. Sounds like his are in Bash.
If you want, you can go to one of my plants.
not too bad.
I don't want to generate. Here you go. Here's an example output from
Yeah.
that.
Like,
So you can see here why I use awk. I just want the
I can-
numbers. So I
I can
use
easily
awk to
share those.
extract from that text file MATLAB. MATLAB is really sensitive about having ASCII and numbers in the same file. It's evil about it. So I use awk to just strip out the numbers. It doesn't matter.
Cut is going to be
You can, anyway, you can use whatever you want. So I said, when you look at the NC dump command and you pull these out, you get three values. You get Northern Hemisphere, Southern Hemisphere, and global.
Okay.
Sorry, Southern Hemisphere, Northern Hemisphere, global. I only care about the global.
Right.
So I take the third number.
Yeah,
So that's what my awk script does. It just takes out the third number.
got it.
But you can, like I said, you can do whatever you want. You plot out the third number, and again, I'll share my scripts with everybody, and that's what you plot as a function of time. So these are ordered in a time series,
Mhm.
and then you can see what it looks like over time.
Yeah. This is the stuff I want to know how to do. I think Sang can run all the models and do everything, but then I think both of us should.
Spoken
be
like a true
playing with the
supervisor.
numbers.
I can do all the model time. I get to do with the fun stuff.
With that, and we can both like dig around. Yeah.
Absolutely. So that's how we generate these diagnostic outputs, these kind of plots that you see here, right? Just from that data. We just plot it up with whatever your favorite plotting tool is.
Because that's short.
So once you've done it once,
I don't think it's
it's all
quicker.
the same, basically. There's nothing to. Yes, Colby.
So for short period planets, you're going to get a lot of.
I just said you're going to get that Proxima Centauri B I showed you, 4,000 orbits times 12. That's how many output ACC files you're going to get for that run. So a lot of data.
So there's nothing you can do to adjust.
You can output the data at slower cadences. There are ways to do that. So let's say you want to output instead of let's say you have an orbit that has 0 eccentricity and 0 obliquity. You can output your output. You can have there's a way to have it generate output in, like every year as an average, or every 10 years as an average if you want. There are ways to do that. So you don't have to output every single month. In these cases, these were the first times that we had really run a totally locked world. And also we did the spin orbit stuff that Tony mentioned before. And I really had to have the monthly output to make sure that everything was right. Because it's very easy to use averaging and get what you think is the right answer, but you really don't know what's happening underneath. So in this case, I was very careful about spitting out every month. But if you know that everything's fine, no, you don't have to do that.
And on the other side of the spectrum, because there is some chatting going on in the chat window, are we going to discuss about sub-DD? So this is to save in a finer temporal resolution than monthly.
Okay, I'll tell you what. We can talk about sub-DD at the end of the day if there's enough interest. In the Q&A this afternoon, we can talk about that if that comes up.
Okay.
It's basically a way to do what we call sub-daily diagnostics. That's what sub-DD means.
Which literally means sub-monthly, though.
Yeah, it means sub-monthly, but we like to confuse our nomenclature in this building.
So it's
If you want to look at weather time scale variability, if you want to make movies,
Yeah.
that's what you need to
So
do.
you can even get.
And it's a pain in the neck with the biggest GCM.
You can get output up to every time step.
Or down to every time step.
Down to every time step, yeah.
So whatever cadence you want, from down to the time step level up to the monthly level, you can get that out if you need it for some reason.
Default is monthly averages.
Default is monthly averages. To use the sub-DD
Monthly
facility,
in quotes, right?
yeah. But the sub-DD facility is a non-trivial facility to use.
Yeah.
And we can talk about it in the Q&A later this afternoon, once we get through the easy questions. Okay. Any other questions about this aspect of the model, the diagnostic output from the model? Something maybe I wasn't clear about, something more you want to know about? As I said, any HEMIS variable that you find in the AAJ file or any of the diagnostic output files, the AJ file, the AJL file, the OJL file, whatever it is, you can plot it up in this manner. Whatever you find that you need to plot, it can be done.
And as we mentioned yesterday, the AIJL files do not have HEMIS variables in them. It is a functionality that we have expressed interest to have, so we might get it soon, or not soon, but we will get it eventually. But thinking about scripts, it's very easy to make a script that takes the calculates the monthly mean manually per layer and then save a profile. I mean, I have a script that I do it in IDL. It's, again, everybody has their own language that they might be able to do that.
But somebody else uses IDO. That's right.
Yeah, everybody uses their own tool that they're comfortable with. So
Use what you started with,
what you're
you
comfortable with.
I stick with it now.
Use what you're comfortable with. Okay. I thought we could discuss a little bit about these spectral files, the radiation files that we have been discussing on and on. And luckily, we have our main radiation person here, Eric Wolf, to help us correct mistakes when we talk about the spectral files. So let's take a look at this document, which you all should have access to if you click on it. I can't click on it because I own this document. That's one of the funny things about Google.
You can hover and then it shows you that clickable link.
Does it let you?
Yeah, click there, click inside. There you go. And then that one is
Oh,
clickable.
that one's clickable. Oh. Okay. Anyway, this is a spectral files document. Everybody should have access to this thing. I should say, no. Yeah, there we go. Perfect. Everybody should have access to this thing. You can see at the top, the gentlemen that have been in charge of these spectral files have kindly put their email addresses. Eric is our main person. Please don't write David until you've talked to Eric, because David has gone to the private sector and has very little interest in receiving queries about the radiation code. In fact, he left us because he got tired of doing radiation for 10 years.
But I'm here for a fee. I'm here for a fee.
For a fee, he would be willing, yes.
That's the private sector.
David is now a well-paid consultant. So take your chances with that. Now, there are some things here that are specific to us. You can see here on line number 2, this document contains details and applicability of various spectral compositions, and they're located on some directory on a machine that you've never heard of, most of you called Discover. It doesn't matter. We can make them available to you. In fact, they are available because you all have them. In fact, if you followed our instructions, you have all of the latest spectral files already sitting on your machines because you downloaded a giant 1.8 gigabyte file that contains everything, by the way. So even though it says that it's sitting on Discover, in fact, it's sitting in your home directory somewhere on your machines, hopefully. In the installation that you did for your for the tutorial, you should have seen a couple lines there, which we didn't talk about, where it tells you, you can tell it which spectral files you want to use. You can see here, it has a name called spectral file LW. That means the long wave part of spectral file. And then there's an aerosol properties long wave spectral file. Now, we do have aerosol properties, and that's because Earth has aerosols in it. If you want to do something very non-Earth that involves aerosols, these aerosol files are off limits. So you'll see in the Socrates run deck that those aerosol optical property files are commented out. If you want to use different kinds of aerosols, in essence, that's a research project, and you will be talking to Eric and Kostas about that, and you will be finding money for them to help you generate those aerosol files. Okay, anyway, there's long wave files and there's short wave files. We'll talk a bit about each of those. Now, if you go down here, it says something that's quite useful. Unless otherwise stated, all spectral files have the following temperature and pressure ranges. Temperature ranges for opacities, 100K to 400K. Temperature ranges limits for gas and continuous absorption coefficients, the K tables. That may not mean much to most of you, but anyway, you can see there that there are temperature ranges over which these spectral files, which are the radiation tables that you need to run the model with, will be valid. You can go outside these ranges, it's no problem. The model most of the time won't complain, but you'll have no idea if the heating rates in your atmosphere are anywhere near correct, and we can't even quantify how bad they are. So try to follow the guidelines. Please don't run an atmosphere that's 600K and then write us and say, why do I get all these errors and why is my temperature structure completely crazy? Because we will have an answer for you. It says here pressure ranges for opacities up to 1 bar. That's not true anymore. This actually should say up to 10 bars in some cases. So maybe I can actually hit it.
I think that's
10 bars, up to 10 bars in some cases.
That's
Which
under
we'll
the,
talk about.
under the caveat of unless otherwise stated. So it's usually stated where it's 10 bars. If it's not stated, then it's 1 bar.
For those people like Daniel Cole that know something about water vapor continuum, you can see that all spectral files use the MTCKD 3.0 water continuum water vapor stuff. We did use caviar. We got a complaint in one of our papers that it wasn't the best thing to use, and we immediately switched over and never went back. It didn't make a big difference in our results, to be honest. Yes, ma'am.
These don't depend on the stellar type?
Getting there.
Oh, okay. Great.
But water vapor continuum is still an active topic of research. So I thought actually we're up to MTCKD 3.2, but
I'm not sure. I know it's 3+, but
yeah, right. So it's not 3.0. Anyway, small difference to that.
Well, probably all the files generated here are from the 3.0. I don't think we've upgraded.
yeah, it's 2.0.
Yeah, I thought, okay, all right. Maybe I'm just wrong about that, but if you're doing very warm atmospheres with lots of water vapor, we do still have the option for the caviar continuum, which is what the Met Office model uses as their standard.
Well,
there
we
have been
have
recent papers suggesting that that's too absorbing.
Okay, we do not. We have the option for a limited number of spectral files. If you want to use it for those which we don't have, it would require Eric to do some work.
No, but David retained the caviar versions of all the things that
He generated. I said for a subset of the number of spectral files we have, it is available, but it is not available for all spectral files. Okay, as it says here, CO2 Rayleigh scattering is included in the spectral files that support atmospheres with a lot of CO2. You all can read all these, so I'll continue. I'll quit reading all this stuff. And there are some references down here which you can see about CKD, MTCKD, caviar, high-tran, all kinds of fun stuff. Where we get some of our numbers for example, CO2 collisional absorption. We tried to tell you where we got it from. CO2H2 and CO2CH4 CIA that we got from a Wordsworth paper from 2017 that Robin graciously gave us the data for.
And we have a relevant question
Yes.
on the chat window. Do you only use the water continua from MTCKD or also CO2 foreign? I have no idea.
Also what?
CO2 foreign?
Foreign?
foreign.
Oh, foreign. No, I think we take them all from Robin's work now, and rather than using the MTCKD version. That's correct. So
From Robin Wordsworth's work, so the
Yeah.
paper that's cited just above.
Speaking of Robin, just on a side note, I saw that on Archive last night. Him and Feng Ding had a paper on Archive advertising a brand new GTM.
is there a line-by-line one?
Yes, that's right.
Okay, so as an aside, they presented about that at HEU, and it's a subtle exaggeration on it's not a line by line doing millions of lines, but rather they have several thousand spectral intervals.
Actually, it was talked about at CCTP3 also, and if you remember, it was Geronimo Villanueva that pointed out why we use K coefficients and we don't do line by line.
Right.
There's some information about generalized Rayleigh scattering here. And there's a little, I mean, it's a lot to read, but it's not that much to read. But you can see here that we have put some guidelines. A word on selecting the appropriate spectral file for your simulations. It says, some atmospheres only offer one option, Titan or the early moon. Other atmospheres offer different multiple options, Archean, Earth, and Mars, which may be confusing. And it's underlined, use the spectral file which mostly matches your desired atmosphere with consideration for the total pressure, the total CO2 amount, the CH4 amount, the presence of H2, the presence of N2O. In other words, don't just randomly pick a spectral file that you think, without reading very carefully what is described there, will work for you, because it probably won't. And then it'll bomb or crash or do something nasty, and you'll write us, and then we'll have to figure out that you used the wrong spectral file.
Or worse, it won't crash, but you just won't get the right answer, and you won't know.
Yeah. You'll find out that your temperature is off by 20 degrees from everything that everyone else has done, and you won't know why.
Or worse, the reviewer will find out.
Yeah.
If you're confused, as Eric has put here kindly at the bottom, if you're unsure about which spectral file to use, please contact Dr. Eric Wolf, and He will help you. But please first read carefully these documents. Like everyone, we are bandwidth limited, so we ask that you read the documentation first. It's not that hard. Hopefully the nomenclature is not too crazy. So I thought we'd just go through a few of these. I won't go through all of them to bore everyone, but this Socrates radiation package comes from the Met Office. That's where we got it from, because David Amundsen, who plugged this into our model, used this with the UK Met Office model when he did his hot Jupiter work there. So by default, there are these default spectral files which you find by default in the rundeck that you ran with the Socrates radiation. And they have very specific limits which are placed here for your knowledge. So read very carefully if you want to use the default Earth-based spectral files, because they have very limited very limited ranges. For example, you don't want to use an M-star spectrum with the default Socrates Earth-specific radiation files. They're highly tuned for the solar spectrum to be fast, in the same way that we tune the GISS radiation to be optimized for the solar spectrum. So be very careful about that. Eric, do you want to say a few words about why we have this thing at the bottom of each of these about a high resolution reference spectrum and why someone might want to use that?
Okay, so for each of the spectral files, we create a high resolution version with, we use 350 intervals, spectral intervals in the long wave and 280 in the short wave, and we use these as benchmark cases, and then we create lower spectral resolution files with the same atmospheric constituents to use for the GCM. So the lower resolution have about a factor of 10 fewer spectral intervals, and this allows them to be naturally much faster, a factor of 10 faster than the high resolution files. So the high resolution files are used generally for 1D offline benchmarking to make sure our low resolution GCM ready spectral files are good enough for us to use. But if you so desired, you could use, if you have enough patience and enough computing time, you could use the high resolution versions with the 3D model if you had some particular application where you wanted to use the high resolution outputs to produce some sort of high spectral resolution outputs to produce some sort of thermal emission spectra from your 3D model, etc. So generally, the high res is for offline 1D testing, and the low res is for the 3D GCMs. But you're not limited. You could use either cases in the 3D model if you have an application that calls for it.
Yeah. Thank you, Eric. So if we go a little bit farther down, how much slower do they?
I mean, it's actually a little bit more than a factor of 10 because it's not just the spectral intervals, it's actually the number of Gauss points in each interval. So the high resolution ones are tuned to not only do they have more spectral intervals, but they're tuned to a higher error tolerance, transmission error tolerance that we were talking about yesterday a little bit, whereas the low resolution ones have been further downgraded in accuracy, but I say that that we've downgraded from a error tolerance of about 0.01% down to 0.1% in the transmission error.
I guess what I meant is like the runtime. For the same number of cores, is it like a factor of 2 or a factor of 10?
A factor of 10 plus.
10 plus.
Oh, okay.
Yeah. Sorry for the long answer for the short question. But
2 lines in the rundeck.
Yeah.
To specify these 280, 350 band files. So very easy for you to do the test yourself. Just swap out the existing ones for those and start running and see how. Come back tomorrow and see if you've gotten through a week yet. Or a month. Socrates is slower than the GISS radiation is because, well, we're using a larger, I guess, I don't know,
right.
Just because we're using a larger number of bands to get appropriate accuracy. But
right.
Whether it's just that or not, or a combination of reasons, it runs more slowly than GISS radiation does.
I think it also has less optimizations because it makes less assumptions about the atmosphere.
Yeah.
The GIST radiation assumes
That's right.
present-day Earth atmosphere, so.
Yeah, and it takes a significant fraction of the total runtime of the model. And so you go to these higher spectral resolutions and probably
very, very slow.
90% of the runtime.
For the Earth case, or the Earth duplicate case, is the one that has the Socrates file that has the least number of spectral intervals. So I'd imagine similar to the GIST native radiation,
These GA7.
yeah, the GA7 ones, they have the 3D ready low res versions only have 6 or 7 intervals in them compared to 30 to 40 for the more difficult M-star spectral files.
Yeah, so I'll talk about those. So David did make some extensions to those initial GA7 Socrates default Earth. And these are some of the first ones he did, these DSA and with DSA files, which have a little bit broader temperature range. That was one of the first things I think he did for us. And then if you go a little bit farther down, he's made versions of those GA7 files that can do M-dwarf spectra. And here you can see that the number of bands have already gone up. So the long wave now has 12 bands, and the short wave has 21 bands. So if you just take the default P1SOM40 Socrates Earth run deck, and you just swapped out those GA7 files for these, you'll get the same results, but the model will run a bit slower, 20–30% slower with these because you're running with more spectral bands. You're sampling the spectrum at a higher resolution, basically, to capture more of the features that show up because you now are allowing M-dwarf spectra also to be used with your
We
data.
do have a small section in Way et al. 2017 talking about the relative speed of running the model with the GIST radiation versus Socrates radiation. And it says using the 40-layer atmosphere, you can do 100 Earth years in approximately 24 hours of wall clock time using 44 cores. Using Socrates in the GA7.0, which is the standard Earth configuration, you get about 100 Earth years in 37 hours of wall clock time using 44 cores. And compared to running the model at the same vertical resolution using GIST scheme, and this is an increase in runtime of approximately 50%, blah, 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 blah. So we had a formula for how that scales. I guess not, but anyway, that gives you some idea that even for an Earth atmosphere, Socrates is about 50% slower than the model is about 50% slower with Socrates than radiation. So you go to these higher spectral resolution files, it slows down quite a bit. But I mean, we're able to do still runs. You just have to be patient.
Yeah, and in fact, you can see how much the radiation is eating up your budget. If you just look at your PRT file, maybe I can take a look here. It should tell us.
You can and do a grep.
Just look here. If I can get in here. It's called radiation. I don't have it here.
Oh, do an NCIP dump -H, the ACC file, and then type grep -I CPU time. Yeah.
There we go. There we go. That's one way. It's also in the PRT file, but this tells you exactly what each component of the model is using in terms of percentage of the total runtime of the model.
So that you have the minutes per day, which is the absolute number of wall time, and then the other numbers are fractions of that number.
Yeah. So in this case, you can see radiation is taking up 50% of the runtime budget of this model.
For this particular month, right?
Exactly.
Because that fluctuates with disk usage. If you end up in some CPU, some cores that are faster than some others, but so you get those numbers per file, and then a very tiny detail. If you use some files to generate an annual mean or a multi-year mean, these numbers are attributes in the NetCDF. They are not variables, so they are not being accumulated. So anything you see in the annual or multi-annual files is going to be the numbers from the very last monthly file used.
In other words, just use this on monthly.
So yeah, just use monthly file. If you really want to find out these numbers in great accuracy, open those month by month and average them yourself. Yes.
I guess I should inform that this diagnostic are not very precise, especially if you do like MPI jobs. I mean, run it on supercomputers, because these times partially take into account the amount of time that some processes are waiting for like other processes to finish. So it may be a little deceptive. It gives you just general picture, but sometimes you might find out like that the times could be significantly different.
Gives you an idea, but if you want an idea.
Essentially, they contain any imperfect parallelization issues that we might have in the model.
Okay, let's take a look at some more spectral files. So as I said, you have to be careful when you use these. Look at the temperature ranges over which they're valid and the atmospheric constituents for which they are valid, because that's important. Here we have some files that David created for us for Archean Earth. We don't know exactly what Archean's Earth's atmosphere was made out of, but we have some ideas from different work that people have done. Stephanie knows, so she can tell us. You can see here that these files contain H2O, CO2, and CH4, and of course, by default, N2, even if it's not a radioactively active gas, it does contribute to line broadening. So up to 1% CO2 for your atmosphere is allowed in these files, and up to 1% CH4. That's it in an N2-dominated atmosphere. If you use values different from that, these files are not valid, and you will get inaccurate results. So be very careful when using specific files. We tell you here what the accuracy is for a temperature range less than 310 K, as you can see here. For the long wave and the short wave, we tell you both. This is another specialized case, up to 1% CO2, present-day Earth or lower CH4 amounts again. So we have several different Archean type atmospheres. Here's one called Vlad's Archean Earth that we have been running. These are with N2O added as an absorber, because Vladimir Arapetian has some ideas about that, and we're working on a paper right now to publish that data. Here's another one where we use up to 1% CO2, 1% CH4, N2 or H2 dominated up to 10 bars. You can have an N2 or H2 dominated atmosphere to 10 bars, and again, 1% CO2, 1% CH4 for these. And you can see in the names of the files that the number of spectral intervals is increased. So in the short wave, now we have 15 bands, and in the short wave, we have 43 bands. The larger these numbers are, the slower the model's going to run. So it's not as simple as thinking, oh, I'll just run this, it'll cover all my cases. Don't do that. Try to find the one that fits your case the best with the lowest numbers in those spectral bands, because the model will run faster. Yeah, you could use this for all of your runs, but your model is going to run much slower than it necessarily needs to for cases where it doesn't need to have so many spectral sampling intervals. Here's another one, 1 to 80% CO2, 1% CH4, N2, CO2, H2 dominated up to 10 bar. Again, this is a very flexible set of spectral files that David wrote.
Broken up into 3 separate, there's a 1 to 20, 20 to 50, 50 to 80.
Right. Read very carefully how these work.
It gets a little confusing.
In this case, all of the long wave files have 17 bands, and the short wave files all have 43 bands. Then we have some Mars through time. Modern Mars, CO2 dominated up to, with H2 up to 10 bars. Not that modern Mars ever had 10 bars, but we did it for other purposes to make them a bit more flexible. And you can see again the number of spectral bands. And then there's a Paleo Mars down here. Again, CO2 dominated with CH4 up to 10 bars. You can see everything that's even included in these, all the CO2 line broadening, CO2 CH4, et cetera, et cetera. It's all in here. And again, you can see this particular set of files has 16 and 46 spectral intervals. Then we have the same kind of files with some N2O. And then we have some more exotic things like Titan. Again, you'll have to read very careful what temperature ranges over which these files are valid. And you can see it's 10 and 14, so it's not so much as before. And then we even have some early moon, because we mentioned that we did publish this paper recently in GRL that for an early transient atmosphere for the moon, and Eric generated some spectral files specifically for that, and you can read about that here. Now, someone asked about the spectra. These are all the available stellar spectra that you can use. If you want to use a different stellar spectrum, you have to contact us if the one you want to use is not here. But first, try to see if there's one here that's close to what you want to use. Because if you don't, and you write us, and we find out that the temperature, the effective temperature for the star is 100 K different for what you want than what we want, we're obviously going to tell you, please read our documentation. 100 K is not enough to make any significant difference in the climate of your world.
Do you have a black body somewhere? No.
No.
So I'm not listed on here. We can do it. It just, you ask me and we can do it. Yeah.
Absolutely.
But Mike, I guess not all the shortwave spectral files were generated for all the stars. So that's find this in the rundeck and
yes, that's right. You have to look in the spectral, in the stellar spectrum directory tree to make sure that the shortwave file associated with this name exists before you try to run it. Yeah, they're not all in here. Basically, a lot of these spectral files were made custom in-house for specific science tasks that we had. So we don't have the spectral file for every single one of these, but it's not difficult for Eric to generate that since he already has all the infrastructure there. It's just that for him to generate those spectral files for every one of these different stellar spectra is a bit too much to expect of. So we don't require that.
A lot of them are already there. Those stellar spectra are already created. All those spectral files are created, but not every star has been spawned into every spectral file. But if you have a need for it, let me know. It's not a big task to make, run them and make new ones, but it's just not something I spend my day making sure every single star is there already. If they're
So
not
we do have
needed.
like pretty good coverage from M to G.
Yeah.
Of things. Maybe it's a little spotty and we have a couple of K stars.
Yeah, we added for Nancy's Land Planet project, we added a number of K stars, so that it should be better now. Yeah, we're missing anything hotter than the sun now.
Yeah, we don't have any F stars presently.
Nobody's interested.
Yes, anyway, that's most, I was trying to think if there's anything else. Oh yeah, and there's a table at the bottom of the document that's kind of a summary of everything that is written above, that tells you on the left what the directory in which the spectral file resides and what the spectral file prefix is, so you can dig around and look and see if you can find the spectral file for your favorite spectrum that you're interested in. And that spectrum is listed in your rundeck as, no, I don't remember, solar spectrum, is that it? No one knows.
I don't remember.
I'll look it up here. Yeah, solar_spec is where you put the spectrum that you want to use that I've mentioned here, all of these. So you can see in this case, I'm using solar spec sun_2.9 GYA. And that means that's a spectrum from 2.9 gigayears ago, and we got that spectrum from Mark Clare and his group. Anyway, yeah, so everything is summarized down here. Of course, if you find something that is not clear or something that is missing or some documentation that looks wrong, please write us, because we're infallible, but not always infallible.
Is there a place where all these Google Docs live all together?
Yeah, it's a good question.
And
No,
more,
the answer is no. There's no single place where they all reside.
Really, I thought we had a folder with a lot of them.
I think
it's internal.
it's internal, yeah. But they're accessible. I mean, we probably, you're right, we need to do a better job of.
It wouldn't be, it shouldn't be too much work.
It's very easy to put a link on public to download pages. We should. I think some of these are up there already.
Or make what Gavin has done for the different Google Docs for the Earth model. Have a Google Doc which is a table of contents with links.
Yeah, we could.
Well, we have, I guess, a lot of links from Simplex.
Yeah, but we need to have one place with absolutely everything. Otherwise, it's just covered information.
Thank you, Jade. Yes, you should do that. Please mute your mics if you're online. We can hear whoever's mucking around in their place, or we'll have to mute everybody. Okay. Are there any other questions about the spectral files? I know it's quite technical and there's a lot of information here and it may not be clear. And if it's not, of course, you should bring it up now or this afternoon, or you can write us emails, of course, if there's something.
For context, Eric, maybe you can answer this question as to why ROCKE-3D takes this approach as opposed to the way LMD.
I could comment in on that. I would say most simply accuracy. Socrates is a very flexible model and is also very tunable to whatever accuracy you'd like. The trade-off is the extra step of having to make shortwave spectral files tailored to each star individually. So there's a little bit more work that goes into the front end of setting up spectral files with Socrates, but the trade-off is flexibility and accuracy, and honestly, compared to other radiative transfer codes that I've used and seen, I like Socrates the best from what I've seen because of this. And now for the novice user, it's a little bit more of a pain. You know, to look at. The scripts are more complicated and you're a few levels separated from the nitty-gritty of the code. But now that, you know, David did all the heavy lifting here, putting it into ROCKE-3D and leaving us with a great set of scripts to use, and now that we have these tools in place, it's extremely flexible and as accurate as we want to be, or conversely, if you're not interested in accuracy and you want it to be fast, we can also very easily in the course of a couple days generate a new set of spectral files that tailor to exactly what you want and the precisions that you want. So it's yeah, flexibility and accuracy, to sum it up in 2 words.
Yeah, I want to add to, yes, this is all possible, but it takes Eric's time, and Eric, like everyone else, is overcommitted. So if you have a science proposal you're working on and you expect that you will need very specialized spectral files, I recommend that you contact Eric and add him to your proposal and give him some of his FTE. Otherwise, it's going to be hard for Eric to find time to help you with your very complicated spectral file stuff. And we do that internally. Eric is actually on most of our proposals for funding because we need him for specific sign cases to generate these files for us. So just keep that in mind. He doesn't have an infinite amount of time to generate spectral files for your science cases. And there is some documentation on how to do some of this work, which we can share also. So if you're really into this stuff, we can point you to the documentation that David wrote and that exists within the Socrates group. And you can do it yourself even if you're up for it, and we can give you some guidelines on that.
Yeah, that is true. David left a GitHub directory distribution for how to manipulate the spectral files that I'd be happy to walk anyone through, show them where it is, and give them some guidance through if you're interested in making your own spectral files also.
Okay. So no other questions about that, apparently. For the rest of the day or rest of the morning,
do you want to mention NRAD parameter?
Do I want to mention NRAD parameter? No, I don't think we should mention it. No.
The default value is fine. If we change it, then we'll get the new default value.
Yeah, but I mean, you could make it much faster in certain cases.
I don't think we should mention it.
Nobody wants to know about NRAD. What is NRAD?
So yesterday we did some comparison. We did this comparison yesterday between at least a few of the different run decks. I'm not sure it's really necessary. We could do that in the Q&A this afternoon to compare more things. I think that would be fine if people want to look at that sort of stuff. I think we've covered most of these things. Otherwise,
could we in the Q&A go through like making a planet, go in the planet params and inventing a planet? And
That's the idea for the afternoon.
Yeah,
Oh, great.
we'll do that.
Okay.
That can be in the Q&A. Whatever you like to do, we can do that. And then there are, I have your time permitting, but maybe we'll break for lunch early today, and we can discuss this in the Q&A. But we do have the capability, thanks to Yuka Fuji, who's now at the Earth Life Science Institute in Tokyo, but she was a postdoc here for several years, and she wrote some post-processing routines for the model in which you can generate transmission and reflection spectra. We could try to look at some of that in the Q&A too, time permitting and in what kind of interests there are. There is also a very sophisticated code down at Goddard that's supported by Geronimo Villanueva called Planetary Spectrum Generator. And Ravi Kaparapu and a few other people down there have spent some time trying to find a way to mangle ROCKE-3D NetCDF output files to be used by PSG. I've actually seen some results from that work now, and they claim it's working, but I have not seen the published scripts for that. So until then, I don't know.
So yeah, they say
sorry.
that this is working, and we have a proposal that we submitted a few months ago, and they are collaborators. They didn't even want extra funding for that because it is really streamlined. You give them the output, and then they pass it through some magic, and then you get this.
Yeah, so for example, if you have some model output and you want to see if JBoST will be useful for detecting what you're interested in, yeah, PSG can tell you that. It's very, very powerful. So the stuff that Yuka wrote is pretty basic, but the PSG has a lot more functionality. Yes,
so
Stephen.
the idea.
I worked with both Yuka's code and with PSG. When I was using PSG, that was almost a year ago, and there were many steps in order to be able to import the ROCKE-3D output into that. But at that time, what I was looking for was if they had validated or compared the two codes with producing similar transmission spectra. Do you know if they've done that step?
Don't know the answer to that.
I don't know. I would guess no, but I don't know.
Don't know the answer.
Do you know the state of their treatment of phase-dependent variations? I know that's one thing that they've bantered about is with PSG, which is fundamentally a 1D model. How do you rectify the averaging into?
So they do have some way to handle geometry.
Okay.
If that's what you're asking.
Yes, that is what I'm asking.
Yeah. So they do have that, because I remember in the proposal we wrote, we explicitly said that we can handle different geometries and get different spectra and that, but I don't know all the details about it.
Tiffany Jensen's also been working on her own code to do this well. I've been working with her, so I think she's going to be here next.
She will be tomorrow.
Okay, great.
Yeah, I mean, the advantage of Yuka's code is that it's fairly easy to use. You basically download Anaconda, you download her GitHub stuff, and you can get it up and running fairly quickly and get transmission and reflection spectra out fairly fast. That's the advantage of using it. It doesn't have a lot of functionality. It has limitations, but she's worked out all the bugs. It does work if you want some basic stuff for your proposal or even papers. So maybe I think we'll break early, and unless there's any other questions relevant to the content we discussed this morning. And why don't we aim to return here again at 2 sharp, and we'll pick up where we left off. And well, we won't pick up where we left off. We'll ask for your questions, and we'll try to show you how to do things that you've asked about, the best of our time permitting. Okay, see you in 2 hours past noon. Okay, so.